Hi, I'm Scott Knockby. In this video, we're going to look at finding the Jacobian for a spatial manipulator. So by the end of this video, you should be able to derive the Jacobian for a spatial manipulator using joint directions and cross products. So in this example, we're going to use the same manipulator that we did for the previous video where we were doing joint directions and derivatives to find the Jacobian. So we're just going to examine the same robot, but this time we're going to use joint directions and cross products to find our Jacobian. So recall this is a 6 degree of freedom robot. Its layout is R, parallel R, parallel R, parallel P, perpendicular R, perpendicular R. All right, we're choosing that the tool frame is equivalent to frame 6. We have our zero displacement diagram, and we have our modified D and H parameters based on that zero displacement diagram. Again, here are our homogeneous transforms that we find by just taking our D and H parameters and plugging them into the homogeneous transform equation. And like before, we need to find the forward displacement solution. So we have T02, T03, 04, 05, and then finally 06, which is the full forward displacement solution for that robot. Now for the joint directions and cross product method, we previously showed that this is the form of the Jacobian. So if the ith joint is revolute, we take the joint direction Zi cross the vector from the origin of frame I to the origin of our end effector frame. All right, and then the bottom is just our joint direction. If the jth joint is prismatic, we just need the joint direction. Okay, and for this example, just like the previous one, we're going to use that the reference frame is the base frame. All right, but we could choose other frames, but we're going to do the same reference frame for this example. All right, so in order to use this method for our revolute joints, we need to know this R vector. So let's look at that in a bit more detail. All right, so we require the position vector in terms of our base frame from the origin of frame I to the origin of the end effector frame. All right, and what we know is we know the position vector from our base frame to our end effector. We know that from our forward displacement solution. As well, we know the vectors from the base frame to each frame I. Right, and that's from our transforms T01, T02, T03, and so on. Okay, so we can use those two vectors to actually calculate R. So let's draw this out. So say we have frame 0 here. We have frame I here. And we have our end effector frame over here. So we know this vector. All right, that's just P from the origin of the base frame to the origin of frame I. All right, and as well, we know this vector, which is P from the origin of the base frame to the origin of the end effector frame. And we're trying to find this this vector, which is R from the origin of frame I to the origin of the end effector frame. Again, these are all in terms of our base frame. So in this case, our vector R is just simply going to be our vector P from the base frame to the end effector frame minus P from the base frame to frame I. So we can use this to calculate our R vector for each of our revolute joints. All right, we're just going to take the overall position of the end effector with respect to the base frame minus the position of frame I with respect to the base frame. Okay, so let's start looking at each joint in turn. So joint 1 is a revolute joint. So the first thing we need to do is we need to calculate R from the origin of frame 1 to the origin of the end effector frame. All right, so that's going to be P from the origin of our base frame to the origin of our end effector frame minus P from the origin of our base frame to the origin of frame 1. So we get this vector from our forward displacement solution. So if we jump back, this is that vector here. So we can make a note of that this is P from the origin of the base frame to the origin of the end effector frame in terms of frame 0. So we're going to keep using that one. So we'll write that in. And you'll see we have C1L1 plus C12L2 plus C123 S5L2. And then we have S1L1 plus S12L2 plus S123 S5L2. And then we have minus C5 L2 minus D4. All right, so that here is this vector here. Now we need to go look at the transform T01 to find this position vector. So we jump to that, T01, and you can see the position vector is 0. All right, so we know that this is 0. So for this case, our R vector is just equal to our P vector. All right, so now that we have our R vector, we need to do our cross product of our joint direction, Z1 cross R. Okay, Z1 in this case, we're going to get from T01. So let's go to T01. There's Z1. So it's going to be 0, 0, 1. Cross our R vector. I'm not going to write that all out. Okay. But if you do the cross product, you'll get minus S1L1 minus S12L12 and minus S123 S5L2. You'll then get C1L1 plus C12L2 plus C123 S5L2, and you'll get 0. So we have the two pieces of information we need. We have Z cross R here, so we need that. That's the first part of our Jacobian for that column. And then our Z direction, which I'm not going to rewrite again, but it's right here. All right, so we have all the information we need for joint 1. Now let's look at joint let's look at joint 2. So here we're going to have R02 now. frame 2 to the end effector frame. It's going to equal our p vector from the base frame to our end effector frame minus our p vector from the base frame to frame 2. All right, this is the same p vector we just used before. I'm not going to keep writing that out because it's a big mess, but we know that. This one we're going to get from T02. So let's go to T02. All right, and there's our position vector there. So we can put that in. So this is going to be minus L1C1, L1S1, and 0. So we subtract that. And we're going to get L2C12 plus, actually let's just write that. C12 L2 just to be consistent, plus C123 S5 L2. Then we'll have S12 L2 plus S123 S5 L2. And we'll have minus C5 L2 minus D4. Okay, we now need to do our cross product. So we need to do Z2 cross our R vector. Z2 we're going to get from T02. So go to see T02. And there's Z2 there in blue. Okay, 001. So we're going to have 001 for Z2 cross our R vector, and again I won't write it out, but it's right above here. It's right here. And if you do that cross product, you're going to get minus S12 L2 minus S123 S5 L2. You're going to get C12 L2 plus C123 S5 L2 and 0. All right, and so those are the two parts of the revolute joint for the Jacobian we need. We need our cross product here result, and we need our joint direction. Let's look at joint 3, which is also a revolute joint. So we need R03 to the end effector, which is going to be P from the origin to the base end effector frame, from the base frame to the end effector frame, minus P from the origin of the base frame to the origin of frame 3. So we're going to, again, use this vector we already know. We need to go get this vector, so that's going to come from T03. So if we go to T03 here, that's our position vector. So we can go put that in. So it's going to be C1L1 plus C12L2. It's going to be S1L1 plus S12L2 and 0. Subtract those two vectors, and you're left with C123 S5L tool, S123 S5L tool, and minus C5L tool minus D4. All right, now we can do our cross product, which in this case will be Z3 cross R03 to the end effector. We're going to get Z3 from T03. All right, so there's Z3 here in blue, 001 again. So 001 cross our R vector. All right, and if you do that cross product, you'll get minus S123 S5L tool. You get C123 S5L tool, and you get 0. All right, so that's joint 3 done. Joint 4 is prismatic, which is pretty easy. All we need is the joint direction, so we just need Z4. Respect to the base frame, so we're going to get that from T04. All right, and that's our joint direction there, 0, 0, minus 1. So let's just go write that down so we have it. All right, 2 more joints to go, and they're both revolute. So we need to find our R vector first. So R05, the vector from frame 5 to the end effector frame. It's going to be the vector from our base frame to the end effector frame, minus the vector from the base frame to frame 5. Okay, so we need to go get this from, sorry, we need to get this from T05. So this is our position. Okay. So we can write that out. It's going to be minus C1L1 plus C12L2. It's going to be S1L1 plus S12L2. And then it's going to be minus D4. So we subtract those two vectors, and we're left with C123 S5L tool, S123 S5L tool, and minus C5L tool. Okay, we can do our cross product now, which is Z5 cross our R vector. Z5 we're going to get from T05. All right, so here's our Z5 joint direction. So we can write that out. It's going to be S123 minus C123 and 0 cross R. All right, and if you do that cross product, you'll get C123 C5L tool. All right, you get C123 C5L tool. You get S123 C5 L tool, and you get S5 L tool. Okay. And now we need one more joint, joint 6. It's our revolute joint as well. So R06 to the end effector frame. It's going to be P0 from the base frame to the end effector frame minus P from the base frame to frame 6. Well, these are the same vector because our end effector frame is frame 6 for this example. So this product will be 0. Our cross product all right, it's also going to be 0, but let's just write in Z6 so we have that information so we can complete our Jacobian. All right, so Z6 we get from T06. So this is Z6 here. So it would be C123, S5, S123, S5 minus C5. Cross the R vector, which we just said was 0. So obviously that cross product is going to be 0. All right, but now we have all the information. We have the Jacobian calculated. All right, so this is for joint 6. This is the first 3 elements, and the Z is the second 3 elements. Same for joint 5. These are the first 3 elements of that column, and these are the second 3, and so on. So if you were to then write this out in matrix form, this will be your answer. Okay, and remember, each column is one joint. So this is joint 1, joint 2, joint 3, joint 4, which is our prismatic joint, joint 5, and joint 6. And if you compare this answer to the example from the answer from the previous example, where we use we use joint directions and derivatives, you see we get the same answer, which is what you would expect. All right, and keep in mind again that this Jacobian is what we use for our forward velocity solution. Okay, where we have V is equal to our Jacobian times our vector joint rates, Q dot, as well as our inverse force problem, where torques is equal to J transpose F. All right, so just a different way of finding our Jacobian. You can use either method, all right, and you will get the same answer.